So we're ready to start. The subject matter that I have for you today is an implementation of programming techniques that allow me to get really good performance for the game of poker. And I think that you will share with me the conclusion that this allows C++ to beat any language at things like implementing an artificial intelligence engine for the purposes of playing poker. Okay, I should start by introducing myself. You might remember me from having presented at CppCon a few years ago on the subject of metaprogramming. I bring experience from many different things, including financial technologies and automated trading. I have presented at the Chicago C++ users group, where I introduced to the world SU function, and of course that I authored the PokerBotic library where we are going to talk about today. I am a tech lead at Camera Platform, and I remind you that my teammates have a poster that shows how Snap deploys the largest augmented reality in the world for with the use of C++. Okay, I will try to explain to you what are SWAR techniques and present them in the context of an application domain area that hopefully is going to be clear to all of us. And the idea of showing these techniques within useful algorithms is that that's how you see the value that they have. I will have to refer about how genetic programming helped me to accomplish these things. What I would like to do is to get to a point in which you are able to understand how these SWAR techniques can be used for your own applications by showing them within a real application domain. And by doing that, I hope to make the development of SWAR techniques more systematic, so that we don't start from scratch all the time, but we accumulate knowledge as opposed to rediscover it every time. We will see many, many slides. Why? Because every individual technique that I'm going to show you helps very little, but when you have a bunch of them together, they really begin to kick in terms of how they help to get performance and at the same time, ease of programming. Let's start by saying what is a SWAR, SIMD within a register. Because this presentation is aimed towards beginners, I will have to say what is SIMD. It is single instruction and multiple data. That means that you have support on your microprocessor for a vector in which the operations occur on each element of the vector simultaneously in parallel. Now, when you look at normal processor integer register of 64 bits in particular in this presentation, we don't have support for individual element sizes, or we might have some element sizes, but not the one that we really want. This presentation is about how to simulate support for basically arbitrary element sizes. Let's start for going over SIMD architectures. There are many examples, for example, x86-64 AVX or ARM Neon that are currently in vogue. Let's see one example from the times of AVX1, not AVX2, AVX1. You have here that you have some support for 256 data types, which is 8 single precisions or 4 double precisions. But from the point of view of integers, you have support for byte, for 16 bits, for 32 bits, for 64, and perhaps 128 bits. But you don't have, if you notice the inconsistency, support for 256-bit integer arrays. This was an inconsistency that we had to wait from AVX1 to AVX2. Okay. Continuing, what is the support for element sizes? For example, in SSE, you have support for an element size of a byte. So when you add two vectors together, the elements corresponding at the same index within the vector are going to be added, and the result is going to be put in an output. But if any of those additions overflows, what happens is that you're going to get saturation. You're going to put the largest integer value there and not carry into the element with the highest significance. However, all of these in every architecture is very, very inconsistent. It's maddening. Because, for example, in SSC, you have 3 operations to take the most significant bit of the elements and pack them into an integer, but they work for 8-bit bytes, 32-bit, and 64-bit. But the operation for 16 does not exist. So what do you do when your processor doesn't support the element size that you want? Again, you had to use SWAR techniques. That's what we're going to be talking about.
Eduardo, 1 second, please. Can you please try to replug the connection because it's blinking on the slides? Just reconnect from your laptop.
Yes. I hope that if it continues to blink, well, yeah, I don't know what's the problem, but can you live with that? Yeah. All right. So, again, the normal 64-bit integers are going to be treated as arrays of bitfields of smaller elements or smaller integer sizes. 2 examples are 8-bit bitfields or 4 16-bit integers, for example. Now, I want to introduce one word of jargon, which is polymorphic. Polymorphic in this case means that the element size within the array, with the SWAR, does not matter. For example, the bitwise AND operation will do its work, and it will not care, it will not make any difference, it will not spill into, will not cross element boundaries. Now, what we had to be attentive toward all the time is that overflow is not supported, okay? I don't want to be repeating that we're not going to be supporting overflow. That is precisely the whole challenge. Let me give you an example. In two's complement, signed addition, you can fill one element to the value of number 1, which would be all the bits set, all the bits available set. And of course, if you add -1 plus 1, it should give you 0. In the ASCII diagram that I have on the screen, you see that indeed it gives me 0. But there is a problem there, which is that there is a carry escaping outward, disrupting what happens in the other elements in the register. So the little bars that I put are virtual. That's what we are going. That's what we are trying to accomplish. Okay, separation between the elements. That's why we have. That's how we achieve parallelism. All right. Like I've been saying so far, what we really want is to keep this element separated. Okay. To support element sizes when the architecture doesn't give it to us. And there are ways to do this. The general way, and you can cheat because you know exactly the nature of your data, and therefore you don't have to solve the general problem. Okay, why are we going to bother? Because we can have a very large speed up. I'm going to prove it to you with benchmarks in this presentation. Also, intuitively speaking, you can see that the operations most used in these techniques are the cheapest, the fastest. In particular, the ones that I have on the slide, I think that the processor can execute up to 3 per cycle. And well, you can do 3 operations. You might begin to synthesize interesting things with them very cheaply in terms of time of execution. What we're talking about also generalizes to vector architectures. As a matter of course, I will show you a slide in which the compiler got crazy on me because it auto-vectorized and it produced a dramatic performance improvement without me even asking for it. And I also think that I want to talk to people who do work on FPGAs because these operations might be implemented in FPGAs. I also have one, for example, that is something I call next subset that I think conceivably might be incorporated into microprocessors or do it in FPGAs for people that do things like high-frequency trading, processing network packets with FPGAs and things like that. Okay, it has gotten the time that we're going to begin to see some code. The complete application that I'm going to show you calculates equities. The user will supply on the command line 2 cards, and the program is going to tell the user what is the probability of his initial 2-player hold cards are going to either win, tie, or lose a round of Texas Hold'em poker. And to do that, this will be a brute force traversal of every 5 community cards of the 50 remaining. And from each community card, we're going to generate all of the possible 2 cards for the other player of the 45 remaining. I hope that they will get sort of a feeling for the primitives that we're talking about. So the main point of this slide is that we're doing things that are simple. They should be easy to understand. In particular, we're just converting the player input into program data. Hold means player hold card, the 2 cards that the player begins with. And we have a few constants with a few magic numbers that I will explain at the end of the presentation because they are not really important. And of course, we initialize our counters. What we have here is a double loop or a double nested loop, which corresponds to iterating over the communities and then iterating over the other players' hold cards. That's what I am doing. I am doing a little few adjustments. So let's very quickly read this slide. Community is the deposit of the hold on the current community. So this converts the subset of 5 from 50 into a subset of 5 from 52. That's what deposit does. I combine the community with the hold cards of the user, and that gives me 7 cards. With 7 cards, I can do a hand rank that classifies that hand. Now initialize the current hold to 2 bits, representing subsets of 2 elements. And I begin to do by the deposit of those 2 bits that corresponds to a subset between 45 to convert it to a 52 set. That gives me the actual cards. I can put them together with the community, get the classification for the competitor hand. That gives me a code, and that allows me to update the counters. And the iteration is just to get the next subset for the opponent hold cards, and then the next subset for the community. I hope that you see that this should look like natural code, like things that we don't have to think too much about if we had the primitive that I am saying here. What is the performance? Well, if I submit the input of the ace of spades and the ace of clubs, I get those statistics that match the theory 100%. After the presentation, please come to me if you want to see it running for any of user cards that you want. But if you Google for the ways to get the ways to get elements of subsets of 5 elements from a domain of 50, and the ways to get 2 more elements from 45, that's the example that we have of the communities and the player hold cards, that is going to give you something that is over 2 billion. And it took, in this very computer, 18 seconds and change. And I ran the numbers, that's over 114 million classifications per second. And if you further dive into the detail, the 2.9 gigahertz when plugged to the wall, that is 26 cycles. So we're talking that this algorithm is able to classify any hand, basically, taking just 26 cycles. Okay, that goes about whether it works or not. We just saw how we have a budget of 26 cycles per hand classification. would like you to try to accomplish brute forcing these things and see what is the performance that you get. It's probably going to be 2 orders of magnitude off the scale that I am showing here. And I hope that you believe me when I say that the code was natural. Furthermore, to bring more evidence, the very old important C functions of a to I and a string length are implemented in a SWAR technique, just not in an explicit way, so that makes it very hard to understand. So we're going to very quickly dive into a mirror of the glibc on GitHub that I found, and this is the generic code for a string length. What you see here is that you convert a character pointer into a 64-bit pointer, and then this is a discussion of masks and magic numbers and all the whatnot. But here, in this part, is where the null is detected. After the null is detected, then it's a matter of seeing in which position it was, and if it's not detected, this post increment will try with the next 8 bytes. Okay, so we can go back to the presentation, and now we're talking about what is the relationship between SWAR techniques and C++. Well, it is the same relationship that we have in SWAR to the plain C programming language, but improved with generic programming. Our community is one of those that is a performance maximalist, so everything that gives us the top performance is interest to us. And we also have the fine granularity of the control of processing resources that allow us to take advantage of them, including going off C++ into assembler when we need it, or perhaps use the very thin wrappers on the assembler that compilers such as the family of GCC and Clang give us. What is the benefit of generic programming? In my opinion, that it relieves us, the programmers, from error-prone code. And it also allows us to understand better, because the processing surface landscape may change. And with that understanding, we have the flexibility to make everything consistent and incorporate new information without having to go through lots of lines of code that are very delicate and therefore error-prone. The gist of what I am trying to say today is that the efforts to do SWAR techniques have not been systematic, okay? At the reception, there is the opportunity to buy the Hacker's Delight book. I would advise you to do it, but that's just an encyclopedia of techniques. They don't appear in the context of an application that you cannot really understand how to use them, okay? So that's what I'm trying to supply today. On the other extreme, you have chess programming that give you some techniques, but within a very constrained, not without any intent to generalize. You can also see the work by Bossier-Boula, which has been doing the fastest things on many different operations of interest. He combines SWAR techniques with vector architectures, and that's how he obtains the top performance that he obtains. Okay, now I'm going to show you something very simple. That's the whole point. This slide should not give you too much information, but it is just, SWAR is just a wrapper of an integer. And it just implements a few operations, has forwarding them to the equivalent operation on the corresponding integer. Okay, now let's get real. Let's start working toward something of a practical application. Let's try to detect a tree of a kind. And what are we going to do to detect a tree of a kind? We need several building blocks to get there, okay? How to work with sets represented as Bitfields is the first one. Then we have to be able to isolate elements in the array. Remember that a SWAR is always an array. An operation to do a vertical comparison of the count of cards of a particular rank against the number 3 in this case. And the way to calculate the count of cards on a particular rank, that is the population count or the Hamming weight. All right? The representation is going to be very simple. We start I think that the easiest way is that because in the game of poker, the card that corresponds to number 2 is the least valuable, to start with the 2s. And the suites are equivalent, but then we can use any arbitrary ordering. I just chose that the first suit is going to be spades. So the bit index that corresponds to 0, or the bit index 0, corresponds to the 2 of spades, then the 2 of hearts, the 2 of diamonds, the 2 of clubs. If I did it right when I wrote the slide, the bit index 37, starting from 0, should be for the jack of hearts, and obviously the last is going to be the ace of clubs. You can see these in 3 different alternative views that we are going to be using interchangeably. 1-bit field of 52-bit elements, 13 4-bit ranks, or 4 striped arrays of 13 bits that corresponds to the suits. And the stripe of that striped array is going to be always 4. Okay, this just is the one slide that I need for people who don't know Texas Hold'em poker, that there are community cards that the players can virtually use to make the better hand, and the exclusive cards. Those exclusive cards are the pocket or the whole cards. And then what is a player hand? It is the combination of the community and the player whole cards. That's why I put it in yellow at the bottom. Okay, 3 of a kind of better requires the things that I am listing in the slide. And that requires us to implement set operations for Bitfields. This is very simple, but I need to go over them to be systematic. Okay, the union is going to be the bitwise OR, the intersection is the bitwise AND, the complement is NOT. To count the number of elements is an operation that we will talk about extensively momentarily. Any that is give me any element in the set, and all and exist, and maybe perhaps iterating over the next subset given one particular subset. Okay, one example of SWAR technique. Let us construct a mask. Let us construct a value that fills the whole SWAR array with the same constant. Okay. Well, this is very simple. You just specify the constant has an argument, and the size of the elements has a template integer argument. And well, you don't have to do the manual counting of how many times and copy and pasting and all that stuff that can be error prone, but especially sometimes you want to generate the corresponding mask for a size of 4, for a size of 8, for a size of 16. You might have the program, but you cannot express it in something has POR, has C, but C++ lets you do it, and this is how I chose to do it for my own code. Okay, now let's go back. The second thing that we need toward the 3 of a kind is to have element access. Unfortunately, because we don't have true access to the elements, we have to recover the techniques of bit splitting, and I have to go over them, okay? So, when we are talking about bit splitting, there is always a mask that tells us what are the bits that we're interested in, okay? If the mask has a position of 0, so in a bit position there is a 0, then we don't care about that bit. But if the mask has a value of 1, then we care about that particular bit. That's all that it means a mask. These techniques were in use for having a background, and from the background, copy a sprite into it and detect whether there was something behind it and moving it and all that stuff. Okay, it's the very same techniques. But again, I want this to be accessible to beginners, and we will go over them. To set 1 to a specific bit, you specify the bits of interest with a mask and use the bitwise OR, and that's going to give you those bits set. To clear to 0, you use the bitwise AND, but with the mask inverted. With the operation of copy from a source to a destination, you have to do several operations. You have to get rid of the things that are not important from the source, and you have to clear the destination on the places that you care about, and that's how it is done. Okay, what is the cost of this operation? 2 masks and 3 bitwise operations, or 1 mask and 4 bitwise operations. And this is very similar to writing memory, which is you read the whole cache line, update that cache line, and write the whole cache line back. Like I said before, this is used to copy a sprite into a bitmap. To flip and negate the bits, because the mask is what tells you what are the bits of interest. It is not a unary operation anymore. It is a binary operation, and the operator that we use is the exclusive OR. And to detect difference compared to a pattern, if you see the exclusive OR and pattern and input, it's gonna be 0 if they are both equal. And from those differences or similarities, you take the ones that you care about by using the bitwise against the mask. That again tells you what are the bits of interest. Okay, guess what? We have acquired the powers of bit splitting. So now we can do the element access, and it's very simple. We use the masking that we have been talking about, and the repositioning with this just to use the shift, in this particular shift, from your perspective, it's going to be shift right, and that puts it in the index 0. See the code for the operation to clear. We don't have to study it. What I want to say is that they are not particularly cheap. We should not be using individual element access because the performance is going to crater there. More jargon, vertical and horizontal operations. The vertical operations generate in the results has many elements, has the inputs. Horizontal combine elements into fewer elements in the output. Examples of vertical operations, the exclusive OR, multiplying by a scalar, we'll see that in a moment. Comparisons, like for example, greater or equal to a constant. We're converting numbers into booleans, but it is the same number of elements, therefore it is a vertical operation. An example of a horizontal operation is when you do the inner product between 2 vectors, that you multiply the corresponding coordinates and then do the summation of those individual coordinate products. So how is C++ helping? I have an example that showed you how building masks at compilation time relieves you from making mistakes. If you change the sizes, then you can get your code to work consistently. And it gives you the flexibility. C++ 14 helps a little bit more because it allows you to program in a more natural way that we're used to. And C++ 17 might help more, but I haven't seen examples. So that's something pending. A very quick overview in ASCII diagrams of multiplication by scale. The key point on this slide is that you can see all of the elements in the array has numbers on a numeric base that is equal to 2 to the number of bits of the element size. And if you had that view, you just apply the normal multiplication algorithm and you see that you're going to multiply it. Again, this does not support overflow. So when you do this, you had to be, somehow you had to guarantee that the resulting products are not going to overflow. The vertical unsigned addition, it is the same thing, okay? Okay, now, vertical sign addition can also be implemented. How? Well, the whole problem is overflow, right? So we can take away the most significant bits of each element and store them away, do the operation, and then in a smart way, accounting for the most significant bits back into the results. That's what that code that I took from chess programming does. The only point that I want to make at this point is that there are very many operations involved here. So that is something that is very probably not practical the majority of the time, but who knows? Okay, now, Boolean SWARs. A Boolean of a register of booleans. We have the need to use only one bit to represent a boolean. So which one are we going to use? I think for many reasons that the most practical choice is to get the most significant bit in the elements. Now we have all of the things that we needed to show you the operation that is going to compare a register of counts of numbers against a compile time constant. Remember, we're talking about the constant of 3 because we want to detect 3 of a kind. So what we're going to have in our particular example is 4 bits elements that have counts from 0 to 4. And what is important here is that if the counts are from 0 to 4, we know it is guaranteed beforehand that the bit that represents 8 is going to be turned off. So that will allow us to play with it. And what is happening here? Okay, in the second bubble, what I am saying is I'm going to make a constant of the most significant bit in the element, okay? I'm going to fill the whole register, and I am going to bleed it in.
No image.
Okay, so what we're doing here is that to set the top bit of each element, and we construct the field with 3 elements, because what we're going to do is to subtract 3 from each count. And now we have the guarantee that none of those subtractions are going to borrow from the adjoining element, because we added virtually 8 to each count. But those that were greater or equal to 3, when you subtract 3, will continue to have that highest bit set, and those that were below 3 will have now the highest bit turned off, and that is our Boolean register. Now, what is the cost of that? To load a constant and 3 of the cheapest operations that the processor offers. With that, which probably should take about 1 cycle, you get all 13 ranks at once. The vector, the 13 booleans at once. Okay, when I want to get any element from the array, I have 2 practical choices. The assembler and the built-ins of GCC and CLAN would, from your perspective, will let us count toward the first bit from the least significant to most significant. That will be the count of the trailing zeros, or counting of the leading zeros, the bit that is most significant in the result. Okay, if we put this together, then this is very, very similar to the actual code to classify a hand in PokerBotic. The first thing that we do is to get the number of counts of repetitions of a rank. That is the population count. We will talk about that momentarily. Then tokes, 3 of a kinds, is to call the wrapper for the operation that we just saw, greater or equal to 3. If the conversion of that Boolean SWAR to a normal Boolean is true, that means that I do have a 3 of a kind, which begs the question of whether I also have a 4 of a kind, and now it is going to be greater or equal to 4. And if I have a 4 of a kind, because there are community cards, 2 players might have this sharing the same 4 of a kind, I need to find what is the highest card of the remaining ones. And I do that by getting the top 4 of a kind. Then I eliminate it by using the clear operation that I showed you before. And it just return, I have a 4 of a kind. The 4 of a kind is that bit. And I can query what is the best, and that's my LR return, okay? So I have fully identified a 4 of a kind in this particular case. Now, if it is not a 4 of a kind, then now we have to query whether I also have a pair. And if I have a pair, then that is a full house, and it goes on. The beautiful thing is that we have now acquired the powers of checking for n of a kind, if we have the population counts. The population counts require their explicit treatment. And what is the treatment that we're going to give it? Well, what it means is to count the number of bits set. The numbers of bits set to 1. It's a combinatorial function. The meaning of a combinatorial function is that the output only depends on the input. And lookup tables are a popular choice to implement combinatorial functions. That means you calculate all of the possible inputs, has indices into a map or typically an array, and for each input you calculate what should be the output and put it as an entry in the array, and then if you want to see what is the result of that function for that input, you go to that particular entry in the lookup table. It's a perfectly sound way to do it. Poker Stove, another good library for poker, uses lots of lookup tables, but I think that because it uses lookup tables, my implementation is faster. My implementation is faster, and I think that's the reason. The problems with implementing combinatorial functions as lookup tables is that in the case of SWARs, implementing several lookups at once is very difficult. You can merge several inputs and make a very big table, but then you end up hitting problems of memory sizes and locality and cache and all that whatnot. The performance just doesn't scale. And you might recur to a specific processor instruction such as p-shuffle bytes. That's like magic, but I cannot talk about it because I ran out of time. So the real problem is that lookup tables put pressure on memory resources that get hidden while on a benchmark, but while running real-life applications, that's there interfering with the rest of the application. So it's good for benchmark, but bad for real life. Take it as you want. The uses of PokerBotic for population count are, of course, to get the 13th rank 4-bit population counts and for flushes. But there's a question. When are we going to be faster using logic to calculate population counts for different SIMD, different element sizes, as opposed to repeatedly calling the built-in processor instruction if it is available? Well, remember that population count also allows the flush detection. This is the logic that I implemented, and it is recursive. And I will prove to you very soon that it is very amenable for compiler optimizations, but the key point here is that if I want to calculate, let's say for example in 64-bit, 2 32-bit population counts, I don't have to do much more than just calculating two 16-bit population counts and combine them. And the implementation of calculating two 16-bit population counts is to calculate two 8-bit population counts and combine them, and so on. And this implementation is the same technique that you can find if you look for population count. It is just expressed in a recursive way because I can afford it, because I have the resources of templates. The key idea, again, is that you recur. Okay, let's see a benchmark between the repeatedly calling the built-in, the assembly instruction that presumably is the fastest way to get a population count, and the use of the logic. So I have a catch-2 benchmark, and that catch-2 benchmark, I'm now scared. That catch-2 benchmark is going to just drive the first function. And I put in yellow the varieties. There is one that is logic, and there's one that is built-in, and there's one that is a SWAR, and that's what we're calling, okay? But this benchmark is really interesting. I want you to observe that to call nibbles that will correspond to the entry for 4 bits, it takes 173 nanoseconds to calculate the 4-bit population counts on a SWAR of 64 bits. However, the built-in, to calculate the population count of the whole of the 64 bits without having to be called repeatedly, takes 175 nanoseconds. Again, if you see the entry for 4, it is 173 nanoseconds, and if you see the entry for the built-in, it is 175 nanoseconds in this laptop. So, we have a throughput of 5.9 SWAR 4-bit population counts that encompass the whole of the 13 ranks per nanosecond. That's faster than the built-in according to the benchmark. And I am thinking, I did something wrong. I am bringing to you freshly baked lies. I smell lies in here. So I had to go back and see what the hell did I do wrong? And I, like any decent C++ programmer nowadays, I bring up the Compiler Explorer, of course. And the Compiler Explorer tells me exactly what I expected. If I call nibbles, which is the population count logic, it will give you exactly the logic that I expected. And if I call the population built-in, it just calls the assembly instruction, and that's it. So I'm now really puzzled, like what the hell is going on? And well, let's hope that the internet works. Don't tell me that. Okay, so okay, so Nibbles has the implementation that I expected. For longs, it has the implementation that I expected. But now, let's look at the implementation for this guy here of actually taking a vector. So this is something that takes a vector of inputs, okay? That's what the benchmark does. It takes 1,021, a vector that has 1,021 64-bit integers. And all I am doing is to consume the result of the population count logic by this exclusive OR and returning the value, right? So the only way for the compiler to generate the valid RV is to execute everything. So the benchmark is kind of sound, but this is what the compiler does with it. So as you can see, this is a recursive specification of a function and not vectorized, but the compiler on its own went and vectorized it from 64-bit registers to 256-bit registers. And not only did the vectorization, but it got absolutely crazy by also unrolling 4 at a time. That's why you see that it is loading 256 bits at a time and doing all this stuff and mulling about. And yeah, then of course, I am doing a gigantic amount of work there because the compiler was able to take the code that was innocently written for 64 bits and blown it out of proportion. There's another thing that is very interesting that Clang did. By the way, GCC doesn't do that. If you want to slow down your code, you compile with GCC. The thing that actually calls the built-in, the Clang implementers have decided, apparently, that the population count in the processor is not really that fast. That for the fast pass, they better do the auto-vectorization and unrolling that I showed you before. And furthermore, for the slow path, if we keep going, you're going to see that the population count instruction appears for the slow path. Like there are not enough elements or they are out of alignment, something like that. I don't really know. This means that I didn't do anything wrong. Okay. This happened. This was something that happened when I was preparing for this presentation. So, how C++ helps part 2? Well, I can express very natural divide and conquer techniques at compilation time. They are very suitable for optimization. You saw what the compiler did in this particular case. Of course, that the benchmark is only representative of itself, but it shows you that these techniques are amenable for very dramatic optimizations. And now, continuing with poker, let's cover the subject of straights. What I'm going to do is to shift the cards one at a time. That is the easiest way to implement this, though I call it simple. This is an ASCII diagram of what is it that I am doing. And if you apply the bitwise AND of all of the columns, then you're going to end up a result that only has 2 ones, because this particular set of cards only had two straights. Okay. When we want to go back to the real life, there are 2 considerations. If you want to make your set of cards color blind, then you just apply greater or equal to 1. We already know that it works and is very cheap. And the rest is not very different to the slide that I just showed you. For the aces, you can bleed them back to the bottom of the SWAR register. Can it be done better? One thing that I benchmarked that doesn't work is to check whether it has a 5 or 10 for an early exit. That is a very high entropy branching that no branch predictor likes, and it just doesn't pay for itself at all. But since I read From Mathematics to Genetic Programming that you can buy outside too, I learned about addition chains, and I came with this code that boils down to this. I would invite you to read it when the slides are available. That's going to be today. And if we go back here, you see that what we have is 4 shifts and 4 bitwise ORs. What we have here is 3 shifts and 3 bitwise ANDs. Sorry, I said ORs, I don't know why, but I meant ANDs both times. Okay, what we have here is that the addition chain technique requires 33% less work. Okay, guess what? Now we can code poker in C++ with great performance. That's the graduation, but that's not the end of representation yet. We can also program any other card game with great performance for that matter. But I have postgraduate programs for you. One of them is to calculate all of the subsets progressively. And let's see an example from sets of 5 elements to generate all of the 3 element subsets. I'm going to start on the left by setting the 3 least significant bits, okay? And I am putting that 0 in yellow for a reason. So the meaning of the 0 in yellow in this slide is that 0 is the first 0 that appears after a 1 starting from the right, okay? If you scan for a 1 from the right, you find a 1, then the next 0 that you find, that's the one that is highlighted with a 0. And the algorithm is to replace that 0 with the neighboring 1 and push the remaining zeros to the least significant positions, okay? This ends when I need to draw outside of my initial 5 elements, and that's why I put it in red. This is what I just explained, and that's implemented in the next subset. I don't have the time to show you the code, but I know that it requires 13 operations. But again, this is something that I would like my colleagues that do FPGAs to tell me if they want to implement it, because it is promising. It is helpful for many set simulations. I don't know if this is an original idea because I haven't found it anywhere, but perhaps it is. The surprising thing is that these 13 operations, because they are so cheap, they benchmark very similarly, not as good, but very similarly to nested loops. So if you want to generate subsets of 3, you had to go through the trouble of writing 3 nested loops, right? Well, this will perform almost exactly the same. Another example. We have 4 minutes remaining, and we're very close to finishing the presentation. Horizontal summation. How are we going to sum all of the elements in a SWAR register? We multiply by a vector that is seen as the numeric base that we're talking about, as a vector is filled with 1s. if we multiply and we use the normal multiplication algorithm, we should get the intermediate products that I drew in my ASCII diagram. And guess what? In the most significant element, we're going to get the summation. This is a technique that Daniel Demire used to write what I think is for a single core general purpose processor, not GPUs, but general purpose, the fastest SWAR available. And because I just have the time budget, I am going to quickly show you that code. And he explains a lot of things, what he's doing. He's not using C++, so he's not expressing this in a recursive fashion. I did, but I don't have the time to show you the code. Point is that what he's doing here is do this trick of multiplication, this trick of inner product that I just showed you. And again, this accomplishes the fastest, in my opinion, a conversion of 8 bytes to integers, to ASCII bytes to integers. In conclusion, what we need is mathematics. And I have reached the end of the presentation. Thank you very much. There are, I think, 2.5 minutes for questions. So if anybody has one. Yes?
You were saying at the very beginning of the presentation about the price in cycles, about the price of checking the combination in cycles.
Yes.
And I guess, you were mentioning probably the Intel CPUs.
Yes.
For example, on ARMS, you could do AND and shift for pretty much free. I mean, it would be of the same cycle. Do you have any plans to check, like, and develop it also for ARMS? Because it could give like even better numbers or really strange numbers.
I'm going to repeat the question. The question is whether I talked about the x86 architecture, and yes, I did, and whether the same things are applicable to the ARM architecture. And the real answer is that who knows, because the performance profiles of any of these operations changes not only between architectures, but between processor models, okay? That's why the C++ flexibility of generic programming is important in particular. But I am, okay, this is the slide that you referred to in your question?
The one with this number 26.
Oh, okay, you got the number, that's great. Yes, so most of the SWAR operations, such as OR, AND, etc., the Intel processor has a throughput of 3 per clock per execution unit, I think. And if I am not finding the slide that you meant, but in general, however, here's the thing, okay? You can do systematically an emulation of all that you need to isolate the elements, okay? And in ARM, you use the resources available in the ARM platform and get it done. It is just that I am very, very familiar with the x86 64. Yes, please.
Do you think we've reached an age that we should stop writing ASIMD intrinsics and just write scalar code and expect the compiler to optimize it for us?
The question is whether we should stop using intrinsics and start using constructs that the compiler hopefully will optimize for us. My answer to you would be absolutely yes. We should stop using intrinsics. Look at what happened. The compiler of Clang decided that using the population count assembler instruction wasn't as fast as doing all of the rigmarole with the vector registers, okay? And that should tell you something, okay? The compilers can do things that you don't expect. it literally happened to me while preparing this presentation. So give the compiler a chance, even if it is GCC. All right, it has been a pleasure to be your host today, and I'm going to be very available for questions after the presentation. Thank you very much.